probably pretty familiar with this from Physics 1051, but I'm going to post it for some review anyway, just for people who might be a little bit uncertain. We have an insulating sphere with radius r, and it has a volume charge density rho. Volume charge density rho means volume. Oops, sorry. Means charge over volume. For a sphere, if it had charge q and radius r, then the volume charge density would be q over 4/3 pi r cubed. Okay, we'd like to find the electric field inside the insulator and outside the insulator. First thing that's important is the fact that it's an insulator, and what we know about insulators is that the charge can't move around. So we're going to assume that the charge is uniformly distributed throughout the volume. We'll do other problems officially in class, but for this 1051 review, we're going to assume it's uniformly distributed. That means wherever the charges are, they stay put and they're spaced out evenly through the whole volume. Something like this. Part of the question asks about a conductor, and we'll talk in a minute about how that's different. So to find the electric field, we're going to use Gauss's law. When we use Gauss's law, we have to draw a Gaussian surface. When we draw Gaussian surfaces, we should pick a shape that matches the geometry of our object. We have a sphere, so our Gaussian surface is going to be a sphere. So let's draw our sphere first. Here's our sphere of charge. We'd like to find the electric field at 3 different places: inside, on the surface, and outside. So here's one diagram, and I'm going to try and find the electric field for r less than r using this idea. And here's going to be my second diagram. I'll use this second diagram to talk about E for r greater than r, and we'll use the threshold case in between the two to find out at the surface. Okay, first part, our Gaussian surface. Let's pick for a sphere. With radius little r. So now I'm going to draw it in each of my two cases. If my surface is a radius inside, so this Gaussian surface is inside, this Gaussian surface is outside. They're both spheres though. That's little r, that's little r. This is big R, and this is big R. Okay, next let's think about our Gauss's law. Gauss's law says that the net electric flux through any closed surface is given by the integral of E dot dA, and it's equal to the amount of charge enclosed by our surface divided by epsilon naught. So let's deal with this integral part first. Since our area is the same shape in both cases, this part of the equation, integral of E dot dA, is going to be the same for both cases. So I'm only going to do that work once. The integral of E dot dA is equal to the integral of E times dA times the cosine of the angle between the electric field vector and the area vector. The electric field vectors point straight out at every place because we have radial symmetry. And our area vector also points straight out of our Gaussian surface. There's our dA. And that's true in both cases. So our area vector is radially outwards, and our electric field vector is radially outwards. Those vectors are parallel, so the angle between them is 0. So that's equal to the integral of E times dA times cosine 0. Cosine of 0 is 1. Our electric field is uniform if we're a uniform distance. So E comes outside, so we're left, so E comes outside. Get E times the integral of dA times 1. The integral of dA is just A, and A is the area of our Gaussian sphere. So that's 4 pi r squared. Okay, that's that part of the equation. Q enclosed is how much charge is enclosed by this pink dotted line. That's the tricky part in this problem. So when my Gaussian sphere is inside my surface, if my Gaussian sphere is in here, it can't enclose all of the charge. It can only enclose part of the charge. If I want to figure out how much, I have to use the idea of charge density. So sticking for the case where my Gaussian surface is inside my sphere, the amount of charge enclosed by my Gaussian sphere is going to be the charge density times the volume of my Gaussian sphere. Okay, the density has a symbol rho. The volume of my Gaussian sphere is 4/3 pi r cubed. So this is the Gaussian sphere. Now I can put that my flux, which is given by this expression, is equal to Q enclosed divided by epsilon naught. So E times 4 pi r squared equals rho times 4/3 pi r cubed divided by epsilon naught. We get some things to cancel in here. 4's cancel, pi's cancel, r squared cancels with 2 of those guys. And we're left with our electric field equals rho, the charge density, times r over 3 epsilon naught. It is a vector and the direction it points is outwards when the charge is positive. Okay, so that's my electric field when I'm inside the sphere. What about my electric field when I'm outside the sphere? Well, I've got this same term for this side of Gauss's law. For my other side of Gauss's law, my Q enclosed is equal to, okay, how much charge is inside my pink circle now? The way I would answer that question would be all of the charge on the sphere is inside that circle. So it's still density times volume, and it's the volume of the sphere, the solid insulating sphere itself. If you were to ask the question, why isn't it density times volume of the Gaussian surface, the Gaussian sphere, it's because between this solid line and this pink dotted line, there's no material here. That's just a vacuum, so there's no charge there. The only charge inside is the charge that's on the insulator. So that's why you use the volume of the insulating sphere. So we've got rho times 4/3 times pi times capital R cubed. So then our flux is the integral of E dot dA, which is E times 4 pi r squared, is equal to our charge enclosed divided by epsilon naught. Okay, we've got some stuff cancels on this side of this equation too. 4's cancel, pi's cancel, and we're stuck with everything else. So then our electric field is equal to rho times r cubed divided by 3 times epsilon naught times r squared. It is a vector and the direction is radially outwards. At the surface, at little r equals capital R, we see that these things reduce to exactly the same expression. So why don't we even do a graph of those things and write in the value. So if we were to do a plot of the electric field as a function of distance from the center, this dashed line shows the radius of the sphere. Inside the sphere, the electric field is proportional to the distance from the center, so that's linear. Once you get outside, it falls off as 1 over r squared. And right here, our maximum value occurs at the surface itself, and that value is equal to the density times the radius of the sphere divided by 3 epsilon naught. And you would get exactly the same value if you plugged in R equals capital R in this equation. So that's good. It's continuous at the surface. Definitely a result we expect. Okay, that's A and B done, plus a little bit extra. We didn't have to do a graph, but we did do a graph. Part C, how would your answer change if the sphere is conducting? Here's where you have to remember what's different about conductors and insulators. So part C, in your conductors, and we're going to assume our conductor is in static equilibrium. In the conductor, the charge is free to move. So that's one thing. Second thing is that like charges repel, so all those positive charges repel. If they repel, where are they going to go to get far apart? It's got to be to the surface. So the picture would now be a little bit different. Here's our sphere. Here's all the charges, and they all have to sit on the surface so they can have the maximum separation. So that's the difference between your conductors and your insulators. We'd still like to find the electric field inside and outside. We'll follow the same process, but I'll see if I can't do it a little bit more quickly. To find the electric field inside, we'll do a Gaussian surface inside. So there's my little r. My big R, of course, is the radius of the whole sphere. I'm going to use my Gauss's law. Net electric flux equals the integral of E dot dA equals Q enclosed over epsilon naught. I'm going to use my same result that I got before for my integral of E dot dA. E times 4 pi r squared equals my Q enclosed. How much charge is inside this green dotted line? Well, remember all the charge goes to the surface, so we can't have any of the charge inside that circle. 0. So the electric field inside the conductor is 0, and that's one of the conditions for conductors in static equilibrium. That's one of the results of this chapter. Okay, next, what about the electric field outside? This time we'll draw a Gaussian surface outside. Not the best circle I've ever drawn, sorry. It's got a radius of little r. So my net electric flux is the integral of E dot dA equals Q enclosed over epsilon naught. E times 4 pi r squared, I'll use that same result that we had before. So now, what is the Q enclosed? That's all the charge. So if the charge of this conductor is the same as the charge on my insulator, and I've just sort of set the problem up. I said, how would the answer change if my sphere was conducting? I'm going to assume it has the same amount of charge, the same size, and still a sphere and everything. So for my insulating sphere, rho is charge over volume. So charge is rho times volume. Why don't we put this up here? Charge equals rho times volume. If you were trying to find the charge, which we'd like to have for the second part, rho times 4/3 pi r cubed. So then our electric field is rho times r cubed over 3 times epsilon naught times r squared. And of course that points outwards. This is the same as the insulator. So for our conductor, the electric field inside is 0, and the electric field outside is exactly the same as the insulator. If you wanted to make that graph, then here's your electric field. When r is less than the radius of the sphere, the electric field is 0. As soon as you get outside, it falls off as 1 over r squared. And at the surface, the maximum value it can have is rho times r over 3 epsilon naught.